Okay, let's talk a bit about the certain Unix commands that we're going to be using throughout this course. So I'm just going to present them here, and also in this part of the video I have links to other videos that we have created for you that kind of dive deeper into each command. So I'm just going to very broadly present them here, and we'll have the links in the slides to the other videos that you can access that kind of dive deeper into some of these commands that we're going to be using. Now, please use this kind of as a reference and try to learn more about each command I mentioned here. I won't go over extreme detail on what each command does because it can be very complex, especially with all the arguments, but I just want you to know where to kind of try to look for if you get stuck on an assignment or in just the process of gathering data from a system. So the reason that we use the Unix operating system in this course, apart from it giving us certain good abstractions, like for example the idea that everything is a file in Unix, so even the devices are presented as files, or the network connections are presented as files, or the process state is presented as a file. So because everything is presented as a file in the Unix operating system, and because we have easy tools to work with files, like, and usually you should expect that files will contain text. We have good tools to interact with text files in Unix. So our tools can consume text and also create text as their result. Because of that, Unix-like systems are a good fit both for educational reasons and for actual day-to-day operational reasons when we work with computer forensics. So some commands that I'm going to talk about here have to do with the file system, with the set of files available in our system. And we kind of know that, files can be contained in directories, and directories can be contained in other directories, and there is this hierarchical structure that we can follow. So for example, the command ls that I mentioned here lists files. The command pwd prints a working directory that we're currently right now. The command cd, very prominent, allows us to change the directory that we're executing at. Also the command cp to copy files, or rm to remove files. Then in terms of processes, because we said that the system can have multiple processes running together at the same time, and it looks like it's only running, it's running everything together. So we have multiple processes, so we have the command ps or the command top to kind of examine processes. We might have multiple users, so there are commands like id that shows us the kind of let's say the ID of our user and the ID of the group of our users, and which groups our user belongs in, because there is also the idea of groups. So we might have a user that is in the group of audio, so it allows the user to access the audio subsystem, for example. And then we're also going to talk about a bit how the shell, which the shell is the command interpreter of our system. It allows us, as I said before, to issue commands in a textual way. These commands can consume text files, and they can output text. In that way we can chain commands in a useful way. Let me give an example here. Let's say we have a file that contains, for example, the first, then the last name, then a phone number, for example, and we want, for example, to sort this. This is not a file that is sorted. We want to sort this in a alphanumerical way. Let's say we want to sort it by having the names that start with letter A to be shown in that file before letters that start before names that start with letter W, right? So if that original file was unstructured, we could print that file, so we kind of examine, you know, the file that is unsorted, and then we can give that output to a command that sorts text based on whatever sorting function we give it. So then the output of that command would be again text, but that time that text will be sorted. Now let's say I only want to keep the phone numbers, and so I would like to have only the phone numbers, but of the people that appear in a sorted alphanumerical fashion. Then I can just pass that to another command that only keeps the third field, for example, of that file, and then I would end up with the phone numbers of every contact in my phone book sorted in an alphanumerical way, for example. So this type of operations are enabled in Unix because our tools both accept and produce usually text. Okay, and that's a conscious design decision that you won't find many other operating systems. So for example, the Windows operating system or other operating systems, you know, that are out there don't really push for that idea, and by doing that they're missing an opportunity of having a common structured, let's say a common format for the commands to be interacting with. Of course, you could imagine a system where this idea is taken even further, so we can even add more structure in what we give in or take out of our commands, and that could be even greater. So if in the future you decide to write an operating system, think about problems like that, and maybe your operating system will become super useful as Unix became to many people. So let's talk a bit about the ls command and the stat command. So ls, as I say here, it lists information about files, like the name of the file, the size of the file, excuse me, the creation, action, modification times, the permissions that the file might have. Okay, and then every command every command that we give in Unix, we might also add certain flags, certain parameters, and these parameters change how that command is executed. So for example, when I show here that I might have like ls-l, it might show me the output of ls, but with the creation time included. Or if I say ls-lt, it might also show me the creation and access time, for example. Or if I say ls-a, it might show me what's called a hidden file. Now, in Unix, they're not really hidden files, but traditionally, any file or directory that starts with a dot is not by default shown in the output of ls. So if you want to see it, you should use ls-a. Now that doesn't make really a hidden file, it just makes it in a sense a configuration directory or file, and for that reason this decision was making that whatever starts with dot, I'm going to read as a configuration file or directory, so we're not really going to show it. But you can imagine that in forensics that might be important, right? Because you might want to look into configuration files, or if someone is treating them as hidden files, you might want to look into hidden files. Now on Windows, there is also that concept of hidden files. So through the Windows File Explorer, you might want to right click somewhere and go on properties and might select show hidden files, and that's going to show you more files that are, again, probably configuration files, but someone might be using them to hide data. So we would like to know that. Now there are many different parameters and flags that we give to every command, and at this point I just want to urge you to look into the manual pages. Every command has a manual page. To access the manual pages, you just write man for manual page and then the name of the command. So if I wanted to know the parameters that ls allows me, I would write man space ls, and that would show me the whole manual page of the command ls, and there I would learn more things that I ever want to know about the ls command. For every command that I'm listing here, I'm urging you to look in the parameters, and it is going to be needed for some of the exercises that we're going to give to you. If you see on the bottom of this slide, I have a link to a video that kind of dives deeper into these commands. So please access that video and see the details of the commands, which might be more useful for certain exercises. Again, for this video, I'm just going to brush the surface of these commands. Now, as we said, every user, to list commands, you need to be in a certain path of the directory. Otherwise, every time you list commands, you could list all the list files. Every time you listed a file, you would list all the files on the system. Well, you don't want usually to list all the files on the system. You only want to list the files under a directory that you're at. So when you have that ability, you should also have the ability to change directories. So you can list other files that are in another directory. That's why you use the cd command. Every user at any given time that is executing, or I should say every process at any given time that is executed, is also associated with a directory that the process is in. Now, here I'm mentioning certain other variants of the cd command that are enabled by the shell. So, you have some certain shortcuts to go back to the previous directory that you were, or to navigate directly to your home directory. Every user in Unix tradition has a home directory. There are also commands like pwd to print the current working directory, and commands to copy a file, as I mentioned before, and remove a file. Again, access a video at the bottom of this slide. Now, sometimes you might wonder, how much more space do I have left in this file system? Well, you can use commands like df, which displays the file systems, to see how, what is the free space that you have available and how much space you have used. You might use commands like du that shows again the disk usage, like it lists all the files and how much space they take. And because I said they list all the files, you can also just get an idea of all the files. Like if you want to find out how many files and what are their names under a directory, you might use the incantation like du-a. That's going to show you all the files under the directory that you're at. Now, the size of this file is going to be shown probably in just bytes, but if you want it in a more useful way, like for example, you don't want to see like millions of bytes and you just want to see megabytes, you can use the flag -h, which is going to present it in a human readable format. Now, I kind of hinted before that every file, apart from the actual data in it, has metadata too, like the access modification and change time. I'm going to talk more about that. But if you want to change this access and modification times, you can use the touch command that kind of touches a file, and then you just accessed it because you touched it. So the access time of that file now has changed. But if you touch a non-existent file, well, in the case of Unix, it just happens to just create that file for you. But you could also imagine if you try to touch a non-existent file, it could error. Well, sure. But in the case again of the touch command, it decides to just create the file for you. Again, look at the video listed at the bottom of the slide. Now, we also said that we have multiple processes executing at any given time. So there is a certain set of commands here presented like ps that shows you which processes are executing. Every process is identified by a kind of process ID, like the users that I mentioned before. The users also are identified by user ID and a group ID. So although we can assign names, like when say this process is Firefox, right, or this user is DSP, it doesn't really matter to the system. The system internally cares more about the numerical IDs associated with either the user or the process. And then we have certain versions of this command that can list process just for my user, or for all users, or list the processes and the terminals, because you can imagine that on a multi-user system I might have processes being executed in different terminals, because you can imagine, it might be a server that has like 5 different terminals connected at any given time, and you have 5 users executing one from each terminal. So it's a useful thing to also associate the terminal that something is executing with the rest of the process information. And then we mentioned here the command top. The command top is a text user interface that shows us the currently executing command, and it refreshes every 5 seconds, and we can also see the CPU consumption of the process and the memory consumption of that process easily. But we also have the kill command, which is not really properly named, because you don't necessarily kill a process with the kill command, but you generally can send any signal to a process with the kill command. Sometimes that signal can be the terminate signal, or the hang up signal, but other times it can be any signal, like there are user-defined signals you can send to a command, and depending on what the command listens for in terms of signals, then it might or might not do something. Now, I mentioned before about the user IDs and the group IDs that are actually what the user and the group are for in a system. So using the command ID, you can see your user ID and your group ID. But also there are other commands like W that shows who is logged in the system right now, and the last command, which shows who has logged in the system since whenever the WTMP log, the log of events, has started recording login and logout events. Now, some other types of commands that we have are commands that, as I said before, they deal with searching for data in a file, or sorting a file, or picking a column from a file that is tabulated, or finding a file that might have certain properties in our file system, and all that nice stuff. So here I'm just mentioning the WC, the word count command. You can count the total number of lines on a file, or words or characters. And a famous pairing of the word count command can be with the du-a command. So if you do du-a, it's going to print all the files, one file at every line that is under the directory that you are. And if you count the number of lines on that output, it's going to give you the total number of files. So if you want to find how many files are under a directory, you could take the output of du-a and give it to the input of word count, and that's going to show you how many lines were in the previous output. This way you know how many files you have under a directory. The famous grep command, where you can look for a needle in a haystack, or you can recursively look under a directory for a certain needle. You might say, I want to find all the files in that directory that contain the word box. So every file in that directory is going to look into every file in the contents, and whatever has the string box, but like even if it's just part of a larger sentence, it doesn't need to be separated by spaces. Like whatever has the sequence of POX letters, either in ASCII or in UTF, depending on the encoding that you're running this, it's going to give you back the files that contain the string box. Okay, so you have match box in one file, still contains the string box, so it's going to be matched. Sorry. We talked about the sort command, about sorting based on some sorting function. We talked about kind of cat, where you select a field from a file that has a column form. And finally, there's the find command that kind of can find files based on some property. Like, for example, here I'm listing like find all the files that end in .pdf. Here I have a video at the bottom of the slide that you can also look for details of not just sort but also the rest of the commands mentioned here. Now, as we see, when we run these commands, we might get just too much output. And the shell, the command interpreter, offers us a way to save this output into a new file for further processing. So we can do that by using the redirect operator, which is this larger than sign. So in the first bullet point here, if I run ls-al and redirect that to a file named all files, it's going to create a new file called all files for me that's going to have the output of the ls-al command. I can also do the same thing for if I run the last command and I want to see the past logins. I can redirect that in a new file called /tmp/past logins, and then I can examine that later. Sometimes I might not want to actually create a new file, but I might want to do that thing on the fly. I might want to connect the output of one command to the input of the other one. Well, I can already mention about the du-a pipe to wc incantation. So in that case, you kind of skip the step of creating a temporary file, and the system just changes the output of one command to the input of the other. And it's pretty magical. And then the output of this whole sequence that you will get would be the number of lines that were counted from running du-a. So it will be just a number of files that you have under the directory. Again, check out the WC video for more info. Now, I have to talk a bit here about files. What do they have? Like we can imagine, we said, like for example in the previous slide, we have the file /tmp/last-login. Well, that file has some data in it, and we say the output of the last command in it, right? And we have all the logins on the system persisted there. But also, this file has other information associated with it, like for example the file name, right? I used the file name for that file. I called it /tmp/last-logins. So that's kind of some information that is related to that file. Also, it might have associated some data with which user created that file. Like I might have created that file as the user DSP. Also, it might have more metadata, like when did I create that file, or when did I access that file for the last time, or is it a file or is it a directory? It could be a directory that contains other files in it. So all this extra information, all this metadata, is also packed with a file, and they kind of go together, right, in the file system. Not necessarily, they're not really at the same space, but they are one unit of the file system. So in this example, I have an email, for example, that has certain email headers. It's sent from zen@fix.com to which@porcupine.org. Now, this file that is just a text file that is an email, it might be part of this table that I'm listing here on B, that has like some inodes, and then these inodes, we're going to talk about what an inode is on the file system model, has like access to some blocks of data. Oops, sorry, I didn't mean to change that. Sorry. And then that data is actually persisted on the disk as a sequence of blocks. We're going to talk more about how these things are implemented on the file system module. But what I want you to remember here is that the file is not just the data of the file, it can also be the metadata of the file. So in this case, I'm using the stat command on a file called evidence. The file name is evidence, the size is 36 bytes. It spans 8 blocks, it tells you here. We're going to talk more about on the file system module about that. But what I want you to focus here is that it has certain access time. This file was accessed on the 16th of January of 21. Oops, really sorry, change the slide again. Going back. This file was accessed on the 16th of January of 21 at 1 a.m. 90 minutes. And then I access this file again while I'm running this. I'm saying cat evidence. Cat is just concatenating the file and printing the contents of the file. When you concatenate only one file, it just prints one file. If you concatenate two files, it's going to print one file then the other one as a concatenated output. But in this case, it just prints the contents of that file and says the measurement affects the system. Now if I run stat again, after that, I see that the access time here has changed because I access the file, right? I print the contents, so this action was persisted in the metadata. So we call these sets of metadata timestamps MAC times. It stands for M stands for modification time. Okay, when we modified the contents of the file. Okay, so for example, I added something. I edited the file and I added a dot, for example. The access time, what I just showed you, is when I access the file, when I read it. Every time you read a file, this is persisted on the file system. And then the change time is when you changed the metadata of the file. So, for example, let's say I have a file, I didn't access it, so I didn't read it, and I didn't modify it, I didn't write anything to it, but I changed the owner of the file. I said, this file doesn't belong to DSP anymore, it belongs to Bob. Well, that has to be persisted somewhere. That's the change time. I access the metadata, but I might not have read it or written it somehow. I'm also mentioning things like the number of hard links here. This is a kind of a file system related aspect that we're going to talk more about on the file system module. Now, we need to ask ourselves, when we compare files and when we deal with files, what does it mean that two files are the same? For example, I'm trying to preserve some data. I have some evidence that sits under /path/evidence, and I want to preserve it. I want to put it in /save/preserved evidence. I might have learned about the copy command, the cp command, so I might just say cp /path/evidence /save/preserved evidence. Well, probably, yeah, I did it, right? The contents of the file are there. They have been transferred to preserved evidence. But what about the metadata that I just listed? What would that be? I just created a new file that has a completely new user, a completely new creation time, a completely new access time, right? So I lost that whole part of the story, right? I created a new file that has the data that I want, but I missed all the breadcrumbs that might have been there for me at the file system layer. So sometimes that might be okay, right? I might just not care for it. I might know that the risk is accepted. But other times that can mess up my investigation. So I need a way to compare the files at different layers. I want to compare the content and say that the content is exactly the same as the other content. Or maybe the metadata is the same, the metadata includes the size, or both the content and the metadata being the same. So I want to take all the file system related information. I won't take the inodes that I said before, like the thing that tracks the metadata, I'm going to talk more about in the file system module, and the content of the data as one unit. And then I want to examine it as one unit, right? So what is equality? Again, can be kind of an open question, okay? But we'll talk about certain techniques that we use, like hashing, to kind of feel better about comparing byte streams like files. So here we can talk a bit about hashing.